Hello, welcome to section 4.3, how derivatives affect the shape of the graph. So if you look in your book on page 291, there's this box here that's really important, and it talks about the first derivative test. So the first thing it says we have a critical number. And how do we get critical numbers? Critical numbers come from two things, whether we have the first derivative, figure out where the first derivative is equal to 0, right? Or we figure out where the first derivative does not exist. So those are the places where the critical numbers are. So the sign changes are important here. So if we have the first derivative right here, and the signs change from positive to negative, we have a local maximum. So this would be like an upside down parabola. The slope is positive, 0, and then the slope is negative. So that would be a maximum. It also could be a cusp situation like this, increase followed by decrease, and then that'd be a point of non-differentiability at the top of that curve there, that point. Now the opposite is true. This would be A, and then B would be the opposite, where you would have decreasing and then a stationary point followed by increasing. So that would be a relative minimum right there. Or again, you could have this cusp situation where it's decreasing followed by increasing and the derivative doesn't exist there. Either one of those is a relative minimum because it's the lowest point in that section of the graph. Part C says there's no sign change, and we call these, sometimes we call these saddle points. So where it comes up and then it flattens out for an instant and then goes up again. So that's not supposed to go down. It's supposed to flatten out for an instant in time. So this would be increase, 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 0 derivative, and then followed by increase again. So that would be a place where there's no sign change, and that would neither be a relative minimum or a maximum. So we're looking for the local mins and maxes here, or relative mins and maxes, some books call them. So increase followed by decrease, or decrease followed by increase gives you the max or the min. So we take the derivative, set it equal to 0, or look for where the derivative doesn't exist, and we examine those points and look for sign changes is what we're doing with that. Then concavity is where the second derivative. So right here where it says concavity test, it says if the second derivative is negative, so the second derivative negative, that means the function is concave down. So concave down is like frown. So if I put an A here and do that, right, that's concave down. So it's like an umbrella. It sheds water. So if your second derivative is negative, it's concave down. If your second derivative is positive, then it's like a cup. Up, concave up is like cup. Concave down is like frown. So if your second derivatives, oh, you know what? I just did those backwards. I'm in a hurry, so I did them backwards. Let me change that again. I can't read. This is a little bit blurry for me too. So can you excuse me for that for a second? So if the first derivative is positive, that's A. Okay, let me start over again. So the second derivative is positive, then it's concave up like that. There we go. B is concave down like frown. That's correct. Then right here we talk about the concavity and the relationship to the tangents. So if you have concave up, the tangents are underneath the curve. If you have concave down, the tangents are above the curve. So that's another way to think about how it's changing. Inflection points. An inflection point is where it changes concavity. So that's what's going on in this box here. So when it changes concavity, that's an inflection point. So it's concave up, and then it goes up and switches to concave down. So right there would be the place where it changes the concavity. So that would be an inflection point. All right, so that's an inflection point. So it changes from concave up to concave down. Or you can do this way, concave down switching to concave up. So it changes the concavity. That's an inflection point. For very important that it changes concavity. It's not enough to set the second derivative equal to 0. It must change concavity from positive to negative or negative to positive. The second derivative test tells us about whether there's a local min or max. So part A, I'm going to get this straight this time and not screw this one up. I read through it too fast when I was making the video on that one. So this says it's concave up, right? That's greater than 0 means concave up. So A is concave up, right? And then that means we have a stationary point and concave up. So we have this. So it's a stationary point and it's concave up. That means that that point right there is a local minimum. And then the B is the opposite. This says we have concave down and we have a stationary point because the derivative is set equal to 0. So like this is point C is what they're talking about, point C. Then it is a local maximum. So that's what's going on with that. All right, and I'm sorry about this one. I looked at it backwards and said the wrong thing, but this is correct. So if it's concave up, then it's A, the second derivative is positive, second derivative negative, concave down. I'm not redoing the video for that because I'd have to say all that stuff again. So I always do my videos in one take. So every once in a while I mess something up and you just have to deal with it. All right, so here we go. We're going to find all this information out about this function here. This is a polynomial, and as you know in calculus, polynomials are your friends. Right? Polynomials are your friends because they're easy to take derivatives of, correct? Do you think I can get that little dot out of there? Ooh, look at that. So now it's transparent. It goes over the top. Set vector transparency. Let's see. So I'm still writing here. All right, clear that ink out. So step 1, take the derivative. dy dx is equal to 12x squared plus 6x minus 6. Take your derivative, set it equal to 0. I can divide all of these by 6 to solve it. 2x squared plus x minus 1 is equal to 0. Then we have 2x and then x. So that multiplied together would be 2x squared. And then 1 and 1, right? I'm factoring this. And then this would be positive, and this one would be negative. That should work. Yes, that's factored correctly. Now we do zero product property. We set each factor equal to 0. So out of this first one, x is equal to 1/2, and x is equal to -1. Okay, now we make a sign chart of the derivative. So these are the signs of the derivative. So I'm going to put -1 on here. When x is -1, the function is 0. The derivative is 0. When x is 1/2, positive 1/2, the derivative is 0. So in between the zeros, it's going to be positive and negative, so I'll know where it increases and decreases. Okay, so I'm going to put in a really big number. Let me see, is this marking? Yep, there we go. So I'm going to put a really big number into this parabola. If I put in a big positive number into this, this would be positive. If we put 0 into the parabola, we get negative, so it's negative on this interval. And if we put in a huge negative, that would be positive, so it's going to be positive on this interval here. So the function is increasing on this interval, it's increasing on this interval, and it's decreasing in between. So I just found the increase and decrease intervals, and I just found the local mins and maxes. So it's going to go from increasing to decreasing. That's a mountain, so x is -1 is the place where there's a local max. So the local max happens when x is equal to -1. And the local min is where it's going from decreasing to increasing. That would be x equals +1/2. So those are the places. Now the interval of decrease is on this center interval here. So it's decreasing from -1 to 1/2. And it's increasing on the two outside intervals, which would be -∞ to -1. And then we union from 1/2 to infinity. So that's the interval of increase, that's the interval of decrease, that's where the local max, the local min is. Now we're doing the intervals of concavity. The intervals of concavity have to do with the second derivative. So I start off with the first derivative, take the second derivative. So I go here, and I'm going to take the second derivative off of this. So it's d with a 2 and then a y here, and then dx squared is equal to 12x squared plus 6x minus 6. Oh, wait a second. What am I doing? Mr. Jackie. I'm taking the derivative of this. I just copied it down. Back to here. Okay, so the derivative would be 24x plus 6 equals 0. So take the second derivative, set it equal to 0. So subtract the 6, divide by 24. X is equal to -1/4, because it would be -6/24. Now I'm going to do the sign chart for the second derivative. So we have the second derivative, and then we have -1/4. So 0. All right. So it's -1/4 and makes it 0. So if I put a big positive number into the derivative, second derivative, it would be positive, and it'd be negative over here. So now we know that it's concave up on this interval, concave down on this interval, and it switches concavity at -1/4. So the inflection point is x is equal to -1/4. Intervals of concavity, that's supposed to be -1/4. So then it's concave up on the interval -1/4 to infinity, and it's concave down from -infinity to -1/4. It's supposed to be -1/4. The blue showing up for some reason. Stupid pen tool. Let me move this out of the way as well. Okay. So first derivative is right here. Took it, set it equal to 0. Got these 2 points, made a number line, and I tested the intervals in between. Increase, decrease, increase right here. Then I did the second derivative, set equal to 0. Did the sign chart for this, so it's positive over here, which is concave up, negative over here, concave down. And it switches concavity in between the two. All right. Let's look at a graph of this, and you can see all this stuff. So I typed this into the calculator, and that's what it looks like. So I did type it in, and then this is the graph right here. So you can see that it increases, and then there's -1, so it increases to -1. Then from -1 to, it was a half, right? Yeah, positive a half. So then it decreases to the half, and then after a half, it increases again. The inflection point was at -1/4. And you can see how it does that. I'm going to change this to red and go out here. So there's 1, right? So that's the relative max. There's a half, relative min. And then the inflection point's at -1/4. So about here, it switches from concave down to concave up. The inflection point is typically where the function changes at its most rapid amount. So, oh, I used the magic tool. I don't need the magic pen. I need regular pen. There, max, min, negative a quarter, inflection point, right about there. So it's increasing, decreasing, increasing, concave down, switches to concave up. So that's the deal with that. Now, that's a polynomial. Polynomials are easy. Polynomials are your friends. You kind of understand the way these functions look because you've been studying them since Algebra 2. Let's look at one that's not as easy to understand what's going on. All right, so we're doing the same thing, but we have a more complicated function. We have a polynomial times a log function. So we're going to take the derivative of this using yield. I'm going to put this up here. Actually, I'm going to collapse it, get rid of that out of the way, and then I'll have to remember to bring it up again. Okay, so we're going to use the old product rule. So dy dx is equal to first, second. So the derivative of the first, 2x, times the second, plus derivative of the second, times the first, 2x, natural log, x. Cancels out an x. Okay, equals 0. Also, the domain is restricted on this. You can't take the natural log of 0 or negative numbers. So the domain of this function right away, you should recognize the fact that any answers with 0 involved, right? If you want interval notation, 0, comma, infinity. Anything with 0 or any negative numbers blow up the domain on this, and we can ignore them because they don't even exist in this function. We're going to solve this by factoring, so I'm going to take out the x, leaving 2 natural log of x plus 1 is equal to 0. 0 product proper t, make it t. So we get x is equal to 0, and we get 2 natural log of x plus 1 is equal to 0. Now we have to solve this, so we got natural log of x is equal to, subtract the 1, divide by 2, negative 1 half. So the base is e, so e to the negative 1 half is equal to x. All right, so now I'm going to do the sign chart for this. So we have the signs of the first derivative, and when x is e to the negative 1 half, then it's 0. For time purposes, we're plugging numbers into this, the derivative. If you put in a big positive number, it's going to be positive, so it's increasing on this interval. And then 0 is the boundary over here. It doesn't go past 0. So if you put in a number here, for time purposes, I'm just going to I know that it's negative. So you put in a decimal into here that's on that side of it, and it's negative. So it's going to be decreasing followed by increasing. So we know that that's the relative minimum. So instead of writing these all out, just to shorten the video, I'm just going to tell them to you. So interval of increase, it's increasing above this number right here, decreasing below this number to 0, because after 0 doesn't exist. That's a local minimum because it's decreasing followed by increasing. And intervals of concavity come from the second derivative. So we take the second derivative, which is the derivative of the first derivative. So dy with the squared there, and then dx with the squared here, equals the derivative of this would be derivative of the first, which is 2 natural log of x, plus derivative of the second is 1 over x times the first, so it's 1 over x times the first, which would be 2x, and then plus 1, the derivative of x is 1, equals 0. All right, I need to make the page a little bit longer. That x is canceled, so that's 2 plus 1 is 3, so it's 2 natural log of x plus 3 is equal to 0. And then subtract the 3, divide by 2, so natural log of x is equal to negative 3 halves, and then base exponent answer e to the negative 3 halves is equal to x. And there it is. That's the point, that's the inflection point, because when I do the sign chart on this, this would be e to the negative 3 halves, and then 0 f double prime, the signs of the second derivative, and then 0 is a boundary over here because that doesn't exist past 0. If you put a big positive number into this, it is indeed positive. And then if you put a number on this interval, just for time purposes, I'm just going to tell you that it is negative. So it's going to be concave down on this interval and concave up on this interval on each side of these. I'm going to go ahead and do this live because I do have the graph set up, but it's better to see this live, how this works and interacts. So let me do full page here to summarize what we did here. So we got this, we got the first derivative set equal to 0. On this interval, it's decreasing, followed by increasing, and that's a relative minimum. We took the second derivative and set it equal to 0, solved it. That's the inflection point because it does change from concave down to concave up at that point right there. So I'm going to do this live on the calculator instead of doing it by the graph that's there. So I'm going to go bring up this guy too, and go here, and then zoom. There it is, typed in. I'm going to do zoom and standard, which is number 6. And you can't even see that where it's concave down and concave up. You can't even tell that it's concave up and concave down there. It does look like it's concave up the whole time, and it does look like there's some kind of relative minimum there. I'm going to zoom in once, so I'll go down here, zoom in on 0, 0, and now you can see it better. So you can see that it is concave down here and then it switches to concave up. I'm going to zoom in one more time, and I'm going to change the window so that you can see it over more. So I'm going to put this at 0, and I'm going to change this to 1.25, just doubling what was there, and here. So now these are the important points. Right there is the relative minimum, and that I'm going to hit trace, and that was at second E, which is there, to the negative 0.5 power, the negative 1/2 power. So that's where the relative minimum is. So you can see the function decreases and then it increases. So there's the relative minimum. But the inflection point is very subtle. It's in here somewhere, and that's at second E to the negative 1.5. So right there, it's concave down. You can see it. It's concave down, and then it switches to concave up. So the inflection point's right there, but you'll never see that on Zoom Standard. So the algebra tells me that there's an inflection point at this little blinking thing, but you'll never see it otherwise. So hopefully this has been helpful to go through these. Look through the book, and hopefully that some of this will come alive. Here's the assignment on this section. Oh, this is just showing how the difference between the two graphs. Now you can see so much better. And here's the assignment. It'll be on Google Classroom. Enjoy. This is a behemoth section. Very super important that we go through all these things. Okay, now I need to go here, bring this up, and stop the video.